So this one, there were several questions on. It's a little bit different, but your success was still high. That's interesting. So, but we'll talk about it because there's actually two different ways to approach this. So I'm going to talk about two different ways. Think about this. Yeah. Okay. Here we go. So we got this chain hanging from the ceiling. Okay, and so we're going to want to lift the lower end of the chain so that, what does it look like in the end? It's going to look like this. Something like that. So we're going to lift this lower end up to here. Now, any horizontal movement, there's no resistant force moving something horizontally, so no work is done. So theoretically, you can push something 1,000,000 miles in the horizontal direction, and that requires no work. Okay, so what requires work? When there's force, right? So force, to lift something, you have the resistant force of gravity, and that's its weight. Okay, that's its weight. So in between here, what does it look like? So halfway through, we've gone it's part of the way, right? Part of the way. So let's see. So consistent with what we did would be this. So you've got, this is a typical situation. You're part of the way, typical, right? Okay, and so then you could call this length of chain right here X. The length of chain that you have so far curled up, right? From the very lowest point of the chain to the top of the chain. That length of chain is X. And then what are we going to do? So we need to find the little bit amount of work that we would do for just moving that up a little bit. So we're gonna move that up a little bit of distance, delta X. Okay, so how much work does that take? So this little bit of work is force times the little bit of distance. Okay, and then the force would be what? The weight of the amount of chain that we have, right? The weight of the amount of chain we have. So the weight would be the unit weight times how many feet we have. So what's the unit weight? If 10 feet weighs 25 pounds, then that'd be 2.5 pounds per foot, times the number of feet we have is X. So that's the number of pounds for the amount of chain that we're actually holding on to, right? We're actually supporting 2.5x pounds of chain, and we're going to move that up delta X. Okay, but there's something weird about this. Because, yeah, we're going to move it up delta X, but then when we move it up delta X, what's going to happen down here? We're going to get another delta X of chain at the bottom. See that? So it's like we're going to move it up delta X, but then we're going to gain another delta X of chain. So we really need, what? 2 delta X. So that's kind of tricky. So doing it the way that, similar to our raising our things up, this is what this would look like. And so it's kind of a little bit tricky. So I'm going to show you a different way that's a little more straightforward. But this works. And so then so X is going to go from what to what? So that's our little bit of work. And so then our total work is going to be, so what is X? X is going to start at what? No, X is the amount of chain that we're supporting, right? We're supporting because we're on our way up. It starts at 0, right? So it starts at 0, and then the final value of X is 5, right? At the very end, we'll be supporting 5. Right before it touches the ceiling, we're supporting 5, so it'll be 5. And then it'll be this force times 2 dx. Why? Because you have a dx at the top, and then when you pull it dx, you end up getting another dx in the bottom of chain, more. So it's like we're both lifting it and getting more chain. That's why we need 2 delta x. We need 2 delta x because we're lifting it a little delta x, but then we get delta x more chain. Does it make sense? All right, so the other way to do this is, so any questions on that? All right, the other way I'll do in blue. So the other way is to, I think this is a little bit easier to see, is just instead of thinking of delta x as a little bit of distance, let's make our delta x a little bit of chain, okay? So come down here, so back to the original situation here. Pick a typical link of chain, so like right here. Okay, so that's one typical link of chain. Where do we have to move that piece of chain? Where do we have to, in the end, where was that chain going to end up? Yeah, so reflected across this line, right? Every typical piece of chain will be reflected across this line, so that piece of chain will end up here. So if we got the weight of the link, okay, the weight of the link times the distance we have to move it, right? So force times distance. So the force, the weight of a little bit, so we'll do it over here. So now delta work is going to be what? A little bit of weight times the distance it has to go. So we have to set up our frame of reference here. Frame of reference. So what is x going to be? The easiest way to do is just make x the distance from the center down to that link. And so how far do we have to move every typical link? He wants 2x. Agree with that? So this link up here, how far does it have to go? Does that also have to go 2x? Yeah. So every link is going to go twice its distance from the center to get to where it ends up. So a little bit of weight, one little link, times the distance it has to go is 2x. Now, what's a little bit of weight? Well, that's our unit weight times. Our unit weight's 2 pounds per foot times a little bit of length, delta x. So delta x is like the length of one little link. Again, 2.5 pounds per foot. That's going to give us the weight of one little link, and the distance it has to go is 2x. So then in this case, you get W equals 2.5 times 2x times dx. From what to what? X goes from? The first little link is right here. X equals 0. Last little link down at the bottom, 5. So you see what happens is you get the exact same integral. But 2 totally different ways of thinking about the problem. So do you want to think about the amount of chain that you're supporting and moving that a short distance? Or do you want to think about a little bit of the chain and how far you have to move it? They both end up with the same integral. But totally, 2 totally different ways of thinking about it. Okay, any questions on that problem? All right. So let's try this one. Sheet of paper. You got to be rewarded for coming on a Friday, right? So what I talked about before was we're going to set up a relationship between the height of the beam and then the mass at that point. So what do we know? When the x is 25, so thinking about x, so I'm just going to do it. There are a couple different ways to approach this. I'm just going to do it consistent with what I did last time in class. So I'm going to think about x down from the top. And so when x is 25, what's our total mass? 125? Yes, right? Because it's going to be 100 plus the mass of the strap, which is if it's 1 kilogram per meter, 25 meters, it'll be 25. So you got a mass of 125. You could also make this a force column. How would I get force from this? Times 9.8. So you could do mass here or force, just as long as you eventually do it, okay? And then the other thing we know is that at x equals 0, what is our total mass then? The 100. So we need a linear relationship. The rate of change is change in mass over change in distance. So we got what? 25 and 25. So the rate of change of the mass with respect to x is 1 kilogram per meter. Which makes sense because it's only the strap, right? Every time you pull a meter of strap, you have 1 less kilogram to pull up. So the rate of change is still 1. And then the mass at 0 is 100, so you could say that the mass as a function of x is 1x plus 100. So the rate of change is 1, and then when x is 0, we need the mass to be 100. All right, so then a little bit of work would be force times distance. So it's going to be what? Force times a little bit of distance. What's the force? mg. We got our mass as a function of x, so that's going to be that's the mass, 1x plus 100. G is 9.8 and delta x. So that's our little bit of work to pull up the beam delta x, the distance of delta x. Integral then is from what to what? X is going to go from? So consistent with what we talked about last time, it would be 25 to 0 of x plus 100 times 9.8, and then times negative, right? So because our little change is in the opposite direction of x, so negative dx. Just I want to see how we did, if the class and homework taught us well. How many people got that? Oh, lots. You got that integral? Okay, pretty decent, about half, okay? And the rest of you were close, right? Okay, 20, give yourself 20 out of 20. Okay, so hold on. So, question. So with what we did Wednesday and what we did in the homework, like, yeah, so we had a lot of success and we should have? Yeah. The what? No, sure it does. Because where's the strap? The strap is right here. That at 25, it absolutely does. At 25 meters, what was my total mass that I'm pulling up? So that's part of that relationship. And then at the top, then it's 0 kilograms of strap. So it's part of this mass. Yeah, the strap is in there. Other questions? Yeah? Okay, this was the English versus metric units. Remember we talked about that? So if you're in metric units and you have kilograms, that's not weight, that's not force. You need to multiply by 9.8, and that gives you newtons, which is force or weight. In the English system, you have pounds. That's weight, that's force. There's no mg. English system is pounds. Pounds and kilograms are apples and oranges. If you have kilograms in the metric system, to get weight or to get force, you need to multiply by 9.8. Yep, in the metric system, F equals mg for weight. Okay, can you whisper if you're talking about math? Can you whisper, please? You guys, can you whisper, please? Can you whisper, please? Okay, so in the metric system, we're often given mass in kilograms. That's not weight. That's not force. That's mass. To get weight or force, you need to multiply mg. In the English system, you're given pounds. So mass is slugs. It's obsolete. It's not used. So normally you start with pounds. Pounds is already force. It's already weight. So there's no multiplication to do. Cool. Yeah. Um, because those ordered. I mean, did you have these ordered pairs? Did you have 0, 100, and 25, 125? This equation needs to make these ordered pairs work. So when x is 0, I get 100. When x is 25, I get 125. So it can't be anything else but that. So you've got ordered pairs, and you have a relationship. Okay, can you whisper, please? Guys, whisper. Whisper. That means vocal cords are not vibrating. All right, so does that make sense? So whatever relationship you come up with, it has to satisfy your two ordered pairs that you use to start with. Plug in x to this, you ought to get the corresponding m. Plug in x, you ought to get the corresponding m. So I don't know if your ordered pairs are different. If your ordered pairs are the same, there's no other equation that's going to make those true. One more question. Yes, ma'am. But it's changing, right? As soon when we're pulling it up, the mass of the strap is always changing as we're hoisting it up. Sounds like you're trying to. Why we get what? It's from the two ordered pairs that we have. When x is 0, the mass is 100. Do you agree with that? And when x is 25, the mass is 125. So from those two ordered pairs, we're going to build a linear relationship. Everything. Beam plus the strap. So this makes perfect sense because every time we pull a meter of strap, the mass changes by 1. So that should make perfect sense that the rate of change is 1 kilogram per meter. But it sounds like, I don't know about your method, so I'd have to look at your method. I know there's different ways to do it, but it kind of sounded like you were trying to just take all the mass of the strap and use that. But as we're pulling, the whole point is as we're pulling the strap, the mass is always changing, so the force to pull it up is always changing. And that's why mass is a function of x. It changes with x. Okay, we need to move on. Last question. No, because when x is 0, we want it to be 100, not 125. Yeah. So when x is 0, I get 100. When x is 25, I get 125. I don't understand. Mass times that's the mass for any x hanging chain. That's how much the mass is. Yeah. Let's talk after class because we got to move along. Talk to me after class. No, we have to move on, so please, we can talk about it after class. Okay, sorry. All right, here we go. Yeah, pass your quiz in. Good job on the quiz. All right, here we go. I told you had to be rewarded for coming on Friday. I told you. All right, removing fluid from a tank. Okay, so a couple things first here. The density of what? So we need some density. So these are going to be some work problems. We're removing fluid from a tank. Okay, and so first of all, density of water. So this is metric or English? Metric, right? Metric, okay? And so with metric, you could have a mass density, and if you're given mass density, what do you do to get weight density? Multiply by 9.8. So that's showing that, right? So the mass density of water is 1,000 kilograms per meter cubed. We're going to need weight density, so mass times 9.8 gives weight, or newtons. Okay, what's going to happen with English units? What kind of units are we going to have? Pounds per foot cubed. No extra calculation to do. I should have put that over here. make apples to apples here, over here. And what did I say, 62.5 or 4? 5. Okay, so with density of water, it's automatically weight density, pounds per foot cubed, no multiplication required. Okay, so then the total weight from an amount of water would be the 62.5 times whatever volume of water you have. And that would be the weight. So now, is this English or metric? Clearly it's English, right? That 62.5 is the pounds per foot cubed times whatever volume in feet cubed will give you the number of pounds. Okay, so here's the situation. Circular above ground pool has a diameter of 20 feet and a depth of 4 feet and is filled with chocolate milk, which has a density of 64.3 pounds per foot cubed. How much work is required to move all the chocolate milk from the pool? So the precious commodity does not get wasted, right? All right, so let's draw a picture. Okay, here we go. Draw a picture. All right, and so what, the whole depth of this thing is 4. The diameter is 20. And the whole thing is filled, right? It's blue chocolate milk. Special. Extra good tasting. All right, so what's going to be our approach? We got it. So can we just, basically, can't we just take the weight of all the chocolate milk, which is the force, and then we're going to move it 4 feet? And that's going to be the amount of work to get it out of there? Will that be too much or too little work? That'll be an over or underestimate of the work to get, if we just took all the weight of all the milk and moved it 4 feet and calculated the work for that. Would be shooting too high or too low? Too high because, so only some of the milk has to go 4 feet, and the rest of it doesn't have to go that far, right? Okay, so this is the reason why we need to, this is a more complicated problem than just force times distance, right? Okay, so what's our approach going to be? Work. What about, how are we going to calculate the total work? We're going to start with, thank you, someone's catching on. A little bit of work. We've been doing it for 3 weeks now. Okay. So what do we need? So we need a little bit of work is where we're going to have a certain amount of weight and a certain distance, right? So we're going to have a certain amount of weight and a certain distance that are both constant. So we can just do force times distance, right? So we just want to do force times distance. So we need a particular element where this is possible. What kind of element will be possible for us to calculate the weight and have a constant distance? What kind of element will that be? Can you see it? Trevor. Okay, so what kind of strip? You draw it with your finger, yeah. Yeah, like a layer, right? So a layer. So what about like kind of a vertical strip? Is that going to give us? No, because within that strip, then we have all those different distances it has to go. So what do we need? We need an element that has all the same distance it needs to go. Horizontal, right? So if we take a horizontal strip here, what are we going to get? If we take a horizontal strip layer, what kind of thing do we get? Pancake, right? You thought we were done with pancakes. So if we pick a pancake of water, a layer of water, we can calculate the work for that. Why? Because we can calculate the force and the distance it has to go. So again, let's go from the top of the tank. And our frame of reference from the top of the tank down, we'll call that x. right, so see if you can come up with the expression for the force for that. What's the force to get that, or the work, sorry, the work to get that layer out of the tank, which means getting that layer to the top of the tank is essentially getting it out, okay? So once we get it to the top, then it just spills over the side and we're done, right? Okay? So see if you can come up with the expression for that amount of work that would take to get that layer out of the pool. Go, see if you can do it. See if we've got all the tools. Remember, the force to lift something is its weight. The force in order to lift something is its weight. Okay. Confer. Work together. If you're done thinking, then work together. Okay, how are we going to get the weight? How are we going to get the weight of the layer? Okay, so it's going to be this right here, right? So it's this, but with the right weight density, right? So our weight density is 64.3 pounds per foot cubed times what's the volume of that thing? Pi r squared delta x. Same, it's a pancake, so it's the same as before, a typical pancake, pi r squared delta x. Volume, we need the volume of the pancake. This will be the same as the pancakes we did before. Distance it has to go, in this case, just x, right? The way we've set it up, the frame of reference, it's got to go x. So that means we need to get the radius in terms of x, but the radius is just fixed, right? So what would happen if this thing had slanted sides? The radius would be changing with x, right? And so then r would be a function of x. So we'd need to develop that function, the relationship. But in this case, it's easy. What's r? Just 10, right? Half of the diameter. So we got 64.3 times pi times 10 squared times delta x. So that's the weight times the distance it has to go, x. There's our typical amount of work to get out one pancake of milk. Total volume equals? Okay, so now the order of this, so this is going to be a positive amount of work, right? And so now the order doesn't matter, like we were thinking about pulling the chain up. So here we can think about taking the first layer out first, and then the next layer, then the next layer. So you just do x is 0 to what? 0 to 4. So you don't have that weird thing that you do when you're pulling it up to have to do the reverse and the negative to make it coherent. So here it's just think about, okay, you could start with any layer you want. So we're going to do all the layers starting with 0 all the way down to the 4-foot layer. Questions? Very easy integral then. What we're doing, summing up the amount of work for every pancake layer, right? And this is the work for one pancake layer, right? The weight, which is the weight density times the volume, times the distance it has to go, x. Anybody have a question? Yes, please. Yeah, I just wrote the wrong. Thank you. Yes, absolutely. Thank you. Work, not volume. Yeah, if you sum up little bits of work, you're still going to get work. You're not going to get volume. That's right. Okay, we need to start another example here. Harder one. Questions? Last chance. Okay. So here I have a trough. A trough is like what animals drink out of. Okay, like horses, donkeys, and ponies, and camels. Okay. And so here are the dimensions of it. The bottom dimension width is 60. The top dimension width is 100 centimeters. The height of the whole thing is 50. And it's 200 meters long in this direction. And it's half filled with water. Half filled. What's the work to empty this trough? So we could start by changing everything to meters, okay? So that would be, so we're all doing it the same way. We're going to start by converting to meters. For instance, 200 centimeters is 2 meters. 100 centimeters in a meter. Okay, and then these layers have to get to where to get to empty, to the top, right? So again, let's make x from where x is going to be down from the top. You could make x down from the surface, but then your distance is going to be harder to this is just the easiest way to do it. It's just make x the distance from the top of the trough down. Okay, so see if you can come up with typical amount of work. Take a couple minutes see if you can make any progress on that. So you got to think about how is this different than the last problem. A couple of ways this is different. See how much progress you can make. So first of all, for what, right? So for what? It's going to be a pancake? Okay, so what is the typical element that we're talking about? What will it be like? What's the typical element? Is it a pancake? But it's not a pancake, so how is it different than a pancake? Washer, where's the, no. No, you don't need to do a trapezoid, because like when we did, we did areas, we didn't do trapezoids, what did we do? We still, we still did strips, right? Just rectangular strips, same thing. We didn't do a trapezoid, right? We just did rectangular strips. So you don't have to worry about this thing. When we make things small, a vertical edge will be fine. So what will it be? It'll be like a typical element will be rectangular wafer, like a rectangular layer, right? So it's still going to be a layer, so it all moves the same distance, but it's going to be rectangular. So the force will be the weight of the water of a rectangular layer. Okay, so what is that? That's going to be the weight density, which is 1,000 kilogram per meter cubed times 9.8. That's the weight density. That's newtons per meter cubed times the volume, right? Times the volume of the layer, which would be length times width times height. Times, and so that will be the weight, and then the distance that the layer has to go is, because of our frame of reference, still x. So what's the length? 2 meters. That's that dimension there. So what are we doing? We're doing the volume of this red layer. What's the width of that thing? 0.6. Where am I screwing up here? It changes. Oh, the width changes, right. Yeah, so 0.6 is at the bottom. So this width, what? Is a function of x. The height is, of the layer, delta x. So, again, what we said, linear relationship. Why linear? Because the sides are straight. You need the width as a function of x for the width. And that would be the last thing we need to do. So 1,000 times 9.8 is the what? That's the weight density. We need the weight density times the volume. The volume is length 2 times height delta x. The width changes with x. So we need to build a linear relationship of width with respect to x. And then that whole thing will give us the weight of the layer times the distance the layer has to go. And then we'll integrate from what to what? Our layers will be, the first layer is 25, or 0.25 meters. And the last layer will be at 0.5 meters.